12, oh, you want to, is it on?
Yeah.
Okay. In the 12 minutes, I want to just say a couple of thoughts about Euler's method, and then I'm going to teach you Newton's law of cooling, and it will be done. It'll be just 12 minutes. So really, your task this weekend is to become an expert on these reviews. Your says, Abigail's back. Welcome back. Good. And you know, if you need to get up and run out of the classroom for any reason, you have my permission. You don't have to wait for me. Okay. Not saying that she was suffering like stomach flu or anything, but yeah. Oh, was it food poisoning? Wow. That's serious. Has anyone ever had food poisoning so bad? Okay. Has anyone had it so bad that you actually had to go to the hospital? You have? That's brutal. That's like death. I mean, people die of that.
That's just so.
Really? Wow. Like to bring it out, or?
Yeah, because it was when I was a kid. My mom was like, yeah, just stick something up your butt.
Okay. Maybe it made a bigger impression on your mom than it really was. I don't know. But yeah, I mean, that sort of food poisoning can be deadly, like, wow, like almost die stuff. So good. I'm glad you only had 4 days of pain. Oh my gosh. So it's like 7 days. Wow. Okay, great. Hey, Euler's method. 2 thoughts on Euler's method. Okay. Wow. Here's the first thought, okay? I want to remind you that Euler's method, let's say this is my function f of x, or let's say this is my function f of x, okay? And you'll notice both of these graphs are concave up. One of them is increasing, the other is decreasing. But I want to remind you, with Euler's method, all we're doing is doing linear approximations. It's just instead of choosing one line, let's say I know that guy and I want that guy, instead of just choosing one line, doing the linear approximation of this graph and saying, well, I think my y value is approximately there for this x, we don't choose one line, we actually choose many lines. We go a little bit and then change the line, and then go a little bit and then change the line, and go a little bit and change the line. So we're actually making many linear approximations. So I want you to see, though, that because I'm making many linear approximations, they still are linear approximations, which means my Euler's method is still going to come in below the true answer. You see? My Euler's method, I'm writing these linear approximations that are always getting me below the true answer. And what I just did there is not accurate. Or here. Because I'm stuck on this line. So, yeah, I'm getting that slope, but I'm having to go up like this. And then I get the slope right there, which means I'm going a little bit higher. But I never actually catch up to the graph, whose slope is changing continuously. My lines, my Euler's method lines, just can't keep up. So I want you to see on this graph, Euler's method comes in below the true answer. I'd like you to picture it in your mind. Where is Euler's method's answer going to come in on this graph if I want to find an approximation, you know, for f of c? Is Euler's method going to come in below or above the graph? That is my approximation going to be below or above the true solution? Like, ride those lines. What do you think? How many people say Euler's method is going to give me an approximation above the true solution? Okay, how many people say below? Okay, hey, I'm going to show you. Here's my linear approximation, which gets me below. Then I do another linear approximation, which still gets me below. And I do another linear approximation. I'm using the slopes of the tangents, but I'm stuck there. You see? So I want you to see that I still end up below. So what is it about these two graphs that tells me Euler's approximation is going to be below the true solution?
They're concave up.
Yeah, concave up. And that's the thing I need you to know, something the AP exam people really believe in. And I'm going to ask this question on your next exam. If f of x is concave up, then Euler's approximation will be below or less than the true solution. Because remember, we're just doing an approximation. And it didn't matter whether I was increasing or decreasing. Concave up meant that I came in below the true approximation. How about if my function is concave down? Whether it's like this or like this. Now, what's Euler's approximation going to do? Be above or below the true solution? I hope you're seeing it. Thank you very much, Daniel. Yeah, I hope you're seeing it. It's going to be above. Because now I'm writing this, this guy, and then, okay, I'm going to be with that slope, but I'm going to be up here. So I'm now on that slope, and now I got to be at that slope, but I'm already there. And you see, I'm losing here. Now the slope changes to there, but still, if I wanted f of c, my f of c is going to be above the true solution if my graph is concave down. And it's no different whether I'm increasing or decreasing, right? Here I changed my slope, but I just can never, I'm not doing a very good job of drawing it, but I just can never keep up. I can't keep up with the slope of the original graph, which is changing continuously, Yeah. So if f of x is concave down, Euler's approximation will be above the true solution. So suppose you did a slope field, and the slope field looked like this. Or here, I'll use blue because that's what we're accustomed to. Okay, there's my slope field in the first quadrant. And I told you, hey, I'm going to do Euler's method. I know that 0, y of 0 is equal to 1. I'm going to do Euler's method to find what y of 3 is, let's say. You tell me, is Euler's method going to be above or below the true solution here?
Below.
How many people say Euler's method? I heard a lot of belows. How many people say Euler's method will be below the true solution? Good. What was it about the solution curve that tells you that? Good for you guys. And if you want, just picture or even draw it. Draw the solution. You'll notice those slopes are increasing. So you're going, hey, that's concave up, which means Euler's approximation is going to come in below the true solution. Good. Okay. Well, hey, any questions or comments about this? All right, then the second point I want to make, and I already made it when we were going over our homework, and that is if you double the number of intervals, you cut the error in half. Double the number of intervals, that is cut delta x in half, and you cut the error in half. And I want to remind you, the error ends up being the absolute value between the difference, the absolute value of the difference between the true solution, the true solution and Euler's approximation. The difference between Euler's approximation and the true solution is your error, and you're just cutting the error down. The more intervals, the closer you are to the real answer. And that's my 2 thoughts on Euler's method. Any questions or problems on that? Okay. Well then, hey guys, we're like a week ahead of last year's class. I'm not feeling any great pressure to get things done. So I think we'll just do Newton's law of cooling and the great AP calculus flu on Monday. So don't be absent, because whoever's the last person standing from our AP epidemic gets a prize. Yeah. What's that?
Can it be an A on?
No, it's going to be something like a candy bar. Sorry. Okay, bye-bye.